The new concept is the concept of momentum. The symbol we use for momentum is a lowercase p. The reason we use a lowercase p is not because momentum starts with a p or ends with a p or has a p anywhere in it. It is because a guy by the name of Newton, whom I'm sure you've heard of, came up with coined the term, he used the term impetus, but he used the Latin term, which was patere, and therefore patere starts with a p, so we use p for momentum. And unlike work, where work was very different than what you normally think of as work, the term momentum in physics is very similar to the term that you would use in your everyday lives. Momentum is equal to mass times velocity, where both momentum and velocity have this symbol over the top of them. This means J, that momentum and velocity are both. Remember, momentum and velocity are both vectors. Unlike work and energy, which were scalars, momentum is a vector. It is a boxed equation for today. What are the dimensions on momentum, please? Sean? Which begs the question, what is the base SI dimension for mass? Kilograms. So it is kilograms times meters per second. Notice this is very close to a Newton. A Newton is kilograms times meters per second squared, but it is not a Newton. Also, we do not have a special name for the dimensions for momentum. It is just kilograms times meters divided by seconds. If you could take a moment and add this to your table of friends, this is the only thing we're going to add to the table of friends today, so it's a good moment to add it. The name is momentum. The symbol is a lowercase p. The dimensions are kilograms times meters per second. And the equation is momentum equals mass times velocity, where both momentum and velocity are vectors. Now that we have added momentum to the things that we know, I want to take a moment and look at three different things. Capital P, rho, and lowercase p, which all look very similar when I write them on the board. So I want to take a moment and make sure that you understand the difference between them. So the first one is a capital P. The second one is a Greek letter rho, which looks like a curly P. And the last one is a lowercase p. Capital P, Megan, stands for what? Power. So capital P is power. Who could tell me what rho, the Greek letter rho, stands for? Sarah. Density. So the first one, capital P, is power. The second one is a curly p, it's actually a rho, a Greek letter, which is density. And the last one is a lowercase p, which is momentum. So just to make sure that you identify the differences between those three, and I know sometimes they can get confusing, so I just identify that specifically. Newton's second law. Michael, what is Newton's second law?
Force equals mass times acceleration, where force and acceleration are vectors. Net force?
And it's the net force. Newton's second law, the net force equals mass times acceleration, where force is a vector and acceleration is a vector. Justin, what is the equation definition of acceleration?
Equation vector?
Yeah, what's the equation for acceleration?
Change in velocity over change in time.
The change in velocity over change in time. Delta, change in, is an equation. Dana, what is the equation for delta V, for example? Good, velocity final minus velocity initial. In other words, we have mass times velocity final minus velocity initial divided by delta t. We can multiply through by the mass, and we get mass times velocity final minus mass times velocity initial divided by delta t. What is mass times velocity final? Shua. This piece right here, just mass times velocity final. Momentum final. Notice that is going to be momentum final. And mass times velocity initial is going to be momentum initial divided by delta t. And what then is momentum final minus momentum initial? Austin.
Change in momentum.
The change in momentum. In other words, another way that you can describe Newton's second law is that the net force equals the change in momentum over the change in time. And this is another boxed equation. The sum of the forces equals change in momentum over change in time, where the force and momentum are both vectors. And this gets us closer to the original way that Newton described his second law. It actually was not the net force equals mass times acceleration. It was instead the net force equals the derivative of momentum as a function of time. And this is very close to the derivative of momentum as a function of time. Unfortunately, we can't deal with derivatives in this class. If you do get an opportunity to take AP Physics C, then you will get to learn how to use the derivative of momentum as a function of time is equal to the net force. And that would be Newton's second law. It's very close. This is for the force of impact during a collision. So we now have an equation for the force of impact during a collision. And this marks a moment where we can have a paradigm shift in the way we look at things. And you have seen me do this many times in front of you, but I'm going to do it again. I'm going to take the medicine ball, and I'm going to drop it. Up until this time, the only way we've really been able to analyze this situation is from the moment I drop it until the moment right before it strikes the ground. We've only been able to talk about while it's flying through the vacuum that you can breathe. But today, we can start talking about what happens when it runs into the ground. We can figure out the force of impact during collisions. So this really marks a paradigm shift in the way we can look at things. So we now have to look at two different parts. We have both the free fall portion before it strikes the ground, and then the collision portion where it's running into the ground.